after this session. We move on to bidirectional object-oriented programming.
Hello, everyone. I'm Zhang from Peking University in China. The title of our work is Bidirectional Object-Oriented Programming Towards Programmatic and Direct Manipulation of Objects. This is a joint work with Guanchen, Xiao, and Zhenjiang. Bidirectional programming has two directions. In one direction, users can forward evaluate the input to get the output. In the other direction, users can also modify the output and apply a backward evaluation to the original input and the updated output to get the updated input. For example, we can forward evaluate the left source program to get the right menu bar. Then we can modify the Excel menu item from gray to blue. So the backward evaluation can automatically change the gray to blue in the left program. As a result, this updated program can run again to get this updated output. Researchers have developed many useful languages to achieve bidirectional programming, such as Little Leo, BiX, and lens combinators. They are all functional or relational. As far as we know, there is no study on widely used object-oriented languages. However, in practice, object-oriented languages, many developers are used to develop software such as GUIs using object-oriented languages. So our goal is to design a bidirectional object-oriented language. Object-oriented languages are more complex because of two features. First, they have class inheritance hierarchies. Second, most object-oriented languages are not pure and have references. These two features bring two challenges. So I'll show the challenges concretely using an example. The first challenge is how to handle ambiguity in class hierarchy updating. On the left is a Java-like program. It evaluates to the right menu bar. So in the left, menu class extends the menu item class, and file menu is a menu object, and it invokes the setTitle method, which is inherited from menu item class. This method concatenates this argument T with 3 dots. So this method invocation will generate this file F and 3 dots on the right. Then, if we modify the 3 dots to a square bracket, there are several ways to update the class hierarchy to accommodate this update on the output. First, we can changing the setTitle method in menu item by changing the 3 dots to a square bracket, which is the most straightforward solution. Second, we can also add an overriding setTitle method to menu class, which concatenates the argument T with a square bracket. In this way, a file menu will call the overriding setTitle method here. Third, we can also add a new subclass named child menu to extend the menu class and override this new setTitle method. And then we also need to change the type of the file menu from menu class to child menu class. In this way, file menu will call the setTitle method defined in the child menu class, right? Through this example, you can see there is a huge ambiguity in class hierarchy updating, so it is essential to reduce it. The second challenge is how to handle references. In the same example, color is a reference that can be read and written many times and can be accessed anywhere in the program. So here is just a simple demonstration. Oh, okay. So color is assigned white here, and the file menu uses it to set its color. Then color is overwritten to gray, and this Excel menu item uses it to set its color. So if we change the color of Excel item from gray to blue, we need to find a correct way to reverse the reference computation in the left program, and we need to pay attention to the update order and find which assignment should be updated, right? So we addressed these two challenges, and our main technical contributions can be summarized as these three things. First, we propose a novel bidirectional object-oriented language called BiFJ. We give a new backward semantics that can propagate the updates on the output to those on the source program, where we address the challenges of updating class hierarchies and references. We also prove its correctness. Second, we implement a prototype programming tool called BiOOP to support our language for developing HTML web pages. Third, we demonstrate the usefulness of our language and our tool by successfully bidirectionalizing 11 classic object-oriented applications from a Java Swing tutorial and from GitHub. So now let me introduce how we design our language BiFJ. As the name suggests, BiFJ is derived from a core object-oriented language called Federate Java. Its forward semantics can be found in the book, The Types and Programming Languages. Based on these forward semantics, we give a backward semantics for it, and we prove its correctness. Then, we extend this Federate Java with references, and its forward semantics can also be found in this same book. And we gave a backward evaluation semantics for it and prove its correctness. So these two bidirectional evaluation semantics are our main contributions. Now I'll talk about how to address the challenges. This is about handling ambiguity in class hierarchy updating. Note that we use this class diagram to represent class definitions in the above example. Specifically, the menu class extends the menu item class, which has a method called setTitle, returning an expression T1. After backward updating this method invocation, that a menu object invokes this title method, this left class hierarchy changes to the right one. Next, I will explain how this changes. First, we use a simple strategy called subclassing to create a new subclass named child menu to extend the menu class and override the setTitle method with a new definition T2. Then we optimize this class hierarchy to reduce minimize the changes, and in two steps. First, pull-up methods will lift methods from subclasses to superclasses. For example, we may pull up this setTitle method from child menu to menu class, right? Then we can also continue to pull up this method setTitle from menu class to menu item class. The second step is called collapse hierarchy, which removes empty, newly created classes. We think this is better for developers to understand because the number of newly added classes and methods is reduced. Finally, we prove the correctness in two steps. First, we prove the subclassing strategy is correct. Then we prove this optimization will not change the program's behavior, so it is also correct. Okay, then I explain how to handle references with an example. So this is an initial state which maps references to values, A to 1, B to 2, and LS to an empty list. A colon and an equal sign indicates assignment, and these exclamation marks indicates reading references value from the state. So this code means assigning a list construction of a B's value and LS value to LS. So after this, LS becomes a list of 2, and we assign A's value to B, so B becomes 1 here. And again, we repeat this assignment, so LS becomes a list of 1 and 2. Finally, we output LS, so we get a list of 1 and 2, and this step doesn't change the state. Okay, and we may want to change the first element of this list from 1 to 10, for example, and we propagate these updates back to the program. The big idea is straightforward. It is just to reverse the forward reference computation. And for example, in this last piece of code, we read the LS value from the state. So here, LS value should be a list of 10 and 2. And the next, for this assignment, if we want LS value to be a list of 10 and 2, before this, B's value should be 10 and LS should be a list of 2. Okay, the next step is the trickiest one. So we can easily compute that A's value should be 10 before executing this. However, there is another thing to do. Because we know before this assignment, B's value should be 2 according to this forward evaluation. So we should roll back B's value from 10 to 2. Okay. So finally, LS value becomes an empty list. So to sum up, the important trick is to roll back reference values when we're encountering assignments. And for example, if we don't roll back B's value from 10 to 2, and which means in the initial state B is still 10, then we will output a list of 10, 10 instead of 10, 2. Okay? So these are the formalisms. You can read our paper for a more detailed explanation. And we also implement a prototype programming tool named BiOOP to support our language. And to support directly manipulating an object structure produced by the source program, we adopt a two-stage bidirectionalization. One is between the source object-oriented program and the object structure, and another is between the object structure with the actual output representation, such as HTML code. So the first one, bidirectional transformation, is the core of our work, and just discussed. So for the second one, we build the correspondence between the object structure and the HTML code by adding structure information. Then, in the evaluation, we collect 11 classic benchmark programs of a Java Swing tutorial and reproduce them using BiOOP to demonstrate. Our tool can be used to develop typical GUI programs. So second, to demonstrate the effectiveness of our tool, we conduct a performance experiment by measuring the execution time for the 11 benchmark programs. According to the result, both the execution time of the forward evaluation and the backward evaluation are acceptable. So to sum up, we present the first object-oriented language that can support programmatic and direct manipulation of objects. Theoretically, we carefully extend a core object-oriented language with a backward updating semantics for class hierarchies and references. Practically, we developed a tool called BiOOP for generating HTML documents. We evaluate the usefulness of our tool by reproducing 11 classic object-oriented applications of Java Swing. That's all. Thanks for listening.
Again, please step up to the microphone if you want to ask a question.
So thanks for talk. So you, in the example you mentioned in the references, you showed that you can reverse like the semantics of the list counts. And I believe that if you want to do the same for like other operators, you have to more or less understand their semantics. And also, I think sometimes maybe the reversing is ambiguous, like maybe there are possible ways to reverse it. So how do you handle this kind of like ambiguity, and also how the user can specify or how you know that the reverse semantic of a certain operator?
Yeah, the ambiguity in the backward updating is an important problem in this bidirectional programming scenario, and but maybe this is not our focus in this work. And one way we can search all solutions for the updated program, and in my work, we use a fixed heuristic strategy for like arithmetic expressions. Yeah, so, but this is not our focus in this work.
Mm-hmm. So actually, you just pick one possible solution.
For example, when we updating an addition expression, so there may be many solutions. For example, we can update the first operand, and or we can update the second operand, or we can update both. So in our work, we just choose one solution,
Okay.
but maybe we can search all solutions.
Yeah. And a follow-up question is, for example, if I want to reverse a function call, so because maybe this function is defined as a customized because that's a user-defined method. So is it possible to also reverse this?
You mean what are the specialities?
The point is that if you have like the result of a method invocation, and now I think intuitively reverse is to guess what should the parameters be, the input of this method be. So is it that possible to infer that in this framework?
So actually, the backward updating for function calls is deterministic, and there is no special things for it. We just update the function body first, and then we update the function and the parameters after that. Which means we propagate the updates in the function bodies to arguments and the function definitions.
Yeah, thank you.
Thank you.